We will start the webinar just a few minutes. So good morning from Ottawa. We are about to start the webinar now. Mrs. Elizabeth Adjeleian normally joins us, and she is joining us today. So Mrs. Elizabeth Adjeleian, Professor Paulo, LOURENÇO, distinguished guests, ladies and gentlemen. My name is Jaykumar, and I have the privilege of serving as the Master of Ceremonies for the event this morning. A warm welcome on behalf of the Department of Civil Engineering and Environmental Engineering. Thank you for being present as we celebrate the legacy of Dr. John Adjeleian in a manner that he would have admired through a lecture by a very distinguished engineer and academic. So I'll give a brief brief introduction to Professor Adjeleian, but I would like to respectfully acknowledge at this time that the land from which we host today's program is in the traditional unceded Algonquin territory. So a warm welcome again on behalf of the Department of Civil and Environmental Engineering, and thank you for being present. The annual John Adjeleian Lecture has been established to honor late Professor John Adjeleian, Emeritus Professor of Engineering at Carleton University, for his outstanding contribution to the university and to the profession of civil engineering. I personally had the privilege of knowing John and working with him until from 1975 when we joined Carleton University, both of us at the same time, until he passed away in 2004. John was that rare person who combined the qualities of intellect, creativity, leadership, humility, compassion, and kindness. He touched the hearts and minds of many, and those of us who knew him were blessed in many ways. This annual lecture celebrates the standard of excellence exemplified by Professor Adjeleian. Lectures in the series highlight the outstanding achievements in professional practice, education, and research that have advanced the field of civil engineering. Established in 2003, this is the 18th year that we are holding this lecture, and we had some very distinguished lecturers over these years. After earning a bachelor's degree in civil engineering in 1952 from McGill and an MASc in structural engineering from MIT in 1955, John returned to Canada and set up a structural engineering consulting firm in Ottawa. His firm quickly established a reputation in the city and outside. Over there, it has provided structural consultancy for a large number of projects, diverse structures, some which have become recognized as outstanding examples of architectural and structural innovation. And among them are the Fathers of Confederation Building in Charlottetown, the National Arts Center right here in Ottawa, and the Aviation Museum also in Ottawa, and the Sky Dome, known by different names, the Rogers Center now in Toronto. Structures that John was most proud of, these were the structures. John's firm also designed majority of buildings on the Carleton campus, from the Tory building to the Minto Center to the Canal building, the oldest and the newest, in fact. John joined the then Department of Civil Engineering at Carleton University in 1975, and he served as the chairman of the department from 1976 to 1982, when he took retirement and was appointed Emeritus Professor. During his tenure as chair, he established the department as a center of excellence in teaching and research in the field of engineering. And I'm very happy to report that the department continues to maintain that excellence, has since grown. John was a visionary with a unique ability to visualize how a structural form will work in harmony with the architecture of the building. He encouraged teamwork that brought engineers and architects together. In fact, he was that rare engineer who was admired and loved by the community of architects, and I say rare purposely. Of the many honors that he received, John was proudest of his honorary membership of the Ontario Association of Architects. John had a great love for Carleton and its students. In addition to his service as a faculty member, he also contributed a substantial endowment fund to award scholarships each year to deserving graduate students within the Department of Civil Engineering and the School of Architecture. At this time, I would like to invite my colleague, Professor Paulo, to introduce our speaker and to invite him to present the Adjeleian lecture in 2022. The lecture will be followed by a brief question and answer session. Please submit your questions through the Q&A link on Zoom. The chat will not work. Use the Q&A link on the Zoom, and your questions will be read out by Professor Paulo in sequence, one at a time, for our distinguished speaker to answer. Bora, it's up to you now.
Thank you very much, Jack. So it's my great honor to introduce our speaker today, Professor Paulo LOURENÇO. Paulo LOURENÇO is full professor at the Department of Civil Engineering, University of Minho Guimarães, Portugal, since 2006. He received his degree in civil engineering at the University of Porto, Portugal in 1990, and his PhD in civil engineering at Delft University of Technology, Netherlands in 1996. He has been the head of the Institute in Sustainability and Innovation in Structural Engineering since 2007. His experience in the fields of non-destructive testing, advanced experimental and numerical techniques, innovative repair and strengthening techniques, and earthquake engineering. Specialist in structural conservation and forensic engineering, with work more than 100 monuments and existing buildings, including 17 UNESCO World Heritage Sites. He's also a structural masonry expert, responsible for R&D projects with clay brick, concrete block, and lightweight concrete block masonry and mortar industry. Consultant on innovative masonry structures using confined and reinforced masonry and on masonry infills. He has been the leader of the project team responsible for the revision of Part 1 of the European Code for Masonry. He's the coordinator of the Advanced Masters on Structural Analysis of Monuments and Historical Construction, SAC, since 2007. With the alumni in more than 70 countries and the European Heritage Europa Nostra Award, the most prestigious in cultural heritage in Europe, in 2017. He's the editor of the International Journal of Architectural Heritage and co-advisor of the conference series on structural analysis of historical constructions. He's the author of the books, Historic Construction and Conservation, and Finite Element Analysis for Building Assessment. He supervised more than 50 PhD theses and coordinated multiple national and international research projects. Awarded an Advanced European Research Council grant of 3 million euros to develop an integrated seismic assessment approach for heritage buildings. He's the coordinator of an innovative training network on sustainable building lime applications via circular economy and biomimetic approaches with 15 PhD students across Europe. So now it's my great honor and pleasure to leave the floor for his presentation to Professor Paulo LOURENÇO.
Okay, thank you very much, Bora. Of course, thank you for the invitation to be here. I've been to Ottawa several times, I think the last time in 2018, and I do have many friends there, including obviously Professor Mario Santana, which I know for a very long time, and Professor Bora Pulazzo, which has been a student from our MSc and a very close collaborator. We have been lucky to have excellent students from Carleton, I think about 10 in our international program, and so it's an honor to be here. I'll try to give you in this 50 minutes some brief overview of our work. I will start with some introductory concepts, and then I will address some of the difficulties we have. And I start with a very basic slide. Normally, when we address the built cultural heritage, of course, there are many specialists addressing this topic, and there is a way many components are relevant for addressing the value of anything which exists and has been built. Two of the very important aspects are identity and economy. Identity, it's because we identify with the built environment. And of course, if we have no past, we have no future. And I like very much this sentence of Winston Churchill. He had very interesting, of course, statements, but it is true that we are what we built. The second point is the economy. And so, as you can see in Europe, tourism is a very important contribution to the economy. Portugal is a very small country, not only in size, but also in population. We are only 10 million. I say that, which is true, that at least 50 cities in the world are bigger than Portugal. And so we're really a small country, but we are in the top 20 of world destinations in tourism. And before COVID, we had about 25 million visitors a year, which is really impressive. So tourism is a major source of revenue. Now, of course, that we expect life to have a certain time frame, and buildings, particularly if they are not maintained, they are at risk. And Europeans and Europe somehow has been a little bit the cradle of the theory of conservation restoration. Of course, there's many monuments and important heritage within the European area. And this charter from European architectural heritage states clearly that the heritage is at risk. At risk because of many things, including ourselves, because we are often destructive to the environment, including, of course, the fact that many of these buildings are obsolete, and because I say that deterioration is intrinsic to life. And so anything which is not maintained will eventually die. Now, there are many hazards that affect our heritage. Many are natural, many are man-made. Of course, climate change is a major issue and depends where we are from. For example, I can tell you that we are working in an important building in Mozambique. I can tell you that they have a cyclone, typically there on average in the last 100 years, once every 10 years. Well, in 2019, they have 2 in the same year. This never happened. And since 2019, they had 2 more. And so obviously some areas are much more subjected and will face faster climate change. Also, our destructive power is increasing immensely. And so hazard is not constant. Also, something which is not constant is exposure. And so exposure can mean the built heritage in itself. It can mean the cultural value, which is difficult to assess, of any built heritage asset, but also means people. And so when you have mega cities like we see here, Greater Tokyo is 4 times Portugal in terms of population. You can imagine what will happen if you have a major disaster occurring in these locations. Now there, I think in the last years, I would say maybe since the 90s, sustainability became the buzzword. in our community and across the society, I think two other words became very important in the last decade. One is resilience and the other is risk. And they are aligned together. Now, well, Wikipedia and the internet as an answer to any of our questions. And community resilience is defined there. And basically it has to do about not giving up, about a society being able to perform. Now, a society to perform depends on the built environment. And the built environment is not housing, is not the monuments. Cultural heritage is a small fraction. We're talking a hyper-complex system involving complex infrastructures, electricity, okay, cell phones, gas, water, roads, anything you can think of, hospitals, schools, police. And so we have an important problem then where you have a major disaster, normally cascading effects occur, and let's say damage in one system affects all the other systems. And so we have to look at the built infrastructure in a very, let's say, broad scope and thinking that our one system affects the other. And so resilience is about this graph. If we have a strong event, we can have systems that collapse, we don't want to have. We have systems which are very robust, they go back to the original system. We have systems which are ductile, that they perform adequately with some reduction of performance. And we have amazing systems that even adapt to any change. And this is, again, is a key issue for societies, and it's totally linked with risk. And so here you have a link between resilience and vulnerability, the need to anticipate, to cope with the disaster, to recover to the disaster. And all about this is risk management, and something which is very important implies, as a society, risk governance. This means that our politicians, it means ourselves as a society, need to consider, well, that in order to have resilient societies, we need to manage appropriately risk. Now, risk is a very complex concept because people often mix risk with asset, and people often present risk in a different context. Engineers, I am a structural engineer, trying to look into risk as the product of three things. And these things are the product of hazard times vulnerability times exposure. It's very difficult to change the hazard. For example, obviously, well, you can reduce the earthquake hazard like you're doing, I understand, in your governmental buildings by installing the base isolation. It's very expensive. It's probably impossible to apply to all the buildings. Well, we can change the hazard, obviously, for example, against flood or against blast by introducing protections. But in general, hazard is difficult to reduce. We can also change exposure. For example, we can move people out of the building, limit capacity, and say, well, this building cannot take 1,000 people, but only 100 or 50 or 10 at a time, so that people can escape. And if there is a strong event, you have lower impact. Or you can move in a monument, for example, well, the expensive statues, the amazing, unique paintings somewhere else in a museum to protect them by reducing exposure. This is exceptional. Most cases in engineering, we need to address vulnerability. And so reducing risk means reducing vulnerability. And there is an almost direct relation in this process. Now, there are many different tools, and you cannot use the same tool for a building or for a country or for the world. I will talk about this very, very briefly in a very fast way. Some of the slides I'm going to show you are extremely fast. Now, earthquakes are an important problem for the built heritage. We had a major disaster in our capital in Portugal. We have recurrent disasters in Europe. In any case, this is one of the earthquakes that were involved in Survey. Basically, what you can see is that we have normally rather poor materials. We have local failures because the material disintegrates, because the material is not of enough quality. We have many of these elements that collapse out of plane because they are not properly tied back to something. We have, of course, areas of the building which are much more vulnerable because, for example, if you have a corner, this means that when an earthquake comes from both directions, you are pushing and pulling walls in the corner, and this expels the corner outside. And these are the typical failure mechanisms we have. So buildings tend to collapse out of plane. They kill the people inside, they kill the people outside. And this is extremely fast. So if you have a very vulnerable building, like here you can see an example in a shaking table, if there is an earthquake coming, you have nothing. And if you do nothing, because this is very heavy, this is very fragile, it's in most cases conceived only for gravitational loading, you have a disaster. It's very simple to do better. This is a building which has been done better. We tied it properly to the floors. We strengthened very lightly the floors, and we made it much safer. In fact, this is a building that was tested before and after repair, and we increased its capacity about the double, okay, by a very simple and unexpected, very simple and non-costly intervention. Now, we have this, which is the behavior of an existing building, normally thought for gravity loading and very difficult to withstand major events. And we have this, which is a modern building. And this is a modern building, also made of masonry, very simple. I mean, it's of course a rectangular building. It's actually a very poor building for modern standards, but the quality of the materials are good. And you can see that all the deformation of the building is in plane with these very large cracks in the plane, dissipating a lot of energy by friction. So as the cracks open and close and slide, you have really a fantastic energy dissipation. Well, you lose a little bit of the building. Of course, you lost already a little bit here. You are losing this corner, but this is a fantastic response. Structural engineering is about saving lives and having a risk which is acceptable. And this is a major earthquake. The building is obviously, well, destroyed. Let's say it's not repairable, but doesn't matter, because for this very, very large event, unexpected according to the code, the building survived and it protected property and it protected the people inside and outside, okay? Now, another type of extreme event is blast. And again, blast can be, well, because of negligence or because of a specific target action. Of course, very fast loads can come from impact, from a boat, from a car, can come from, let's say, wars. But this is an example of a test that takes a couple of milliseconds. It's a very fast test. Now, this is very exciting from the structural engineering point of view, because anything you know about earthquake engineering and static loading, so loads that change very, very slowly, you cannot use. So you need to change everything you know. You need to change your tests. You need to change your analysis tool. You need to change the way you think. For example, this is a very famous factor in blast, which is an increased factor taking into consideration dynamics. And you can see that by taking the static properties, which are the properties we use normally in instructional engineering, you get the black line. By changing the correct properties, you change this line where there is, let's say, a permanent deformation in this wall of about 20 millimeters. And by changing totally wrong properties, you get no deformation. And so the response is extremely sensitive to the speed of the blast and to the effects of how the building and how the material responds to this speed, okay? There are many hazards. Fires are a major problem across the world. This is a very famous recent event that everybody forgot, and it was very impactful for a few times in 2019. There are many other strong events affecting our built heritage, and they kill people, they destroy the built heritage. They are a sign that many of our societies are not resilient enough. Now, earthquakes is not the most expensive disaster, but it's the one killing more people, okay? And they tend to kill people very fast. And if you have 200,000 people, 1 million people, or 500,000 killed within a few minutes or a few hours, this is not acceptable for a society. So we have to do something. It's also very interesting to see how society responds to some of these things, because society in general believes landslides are not a big issue, or floods, or fires, or earthquakes. But they think, for example, terrorism. Here you can see a barometer in Europe saying that 90% of the population in Europe believes, terrorism to be a major risk. And you can see that the chance that you die of a terror attack is here. And so the chance that you die is very similar to the chance of being struck by lightning. And nobody is concerned about being struck by lightning, okay? So you can see how the society, all ourselves, respond to social media and incorrect perceptions of risk and incorrect perceptions of threats. Now, another important issue, in my view, from the engineering point of view, is the economics. And disasters tend to be terribly expensive. And when you have a problem in your house, this becomes your problem. When you have a problem in a major disaster, this is a societal problem, meaning we all pay for it. Anybody which is a taxpayer is going to pay for it. And this is becoming impossible to pay. So we need to do better in protecting our world heritage, in protecting our societies. We are failing to address the increasing exponential costs of losses, okay? And we have to solve this very complex problem from an engineering or mathematical point of view, how to combine a very low probability or values close to zero with huge consequences, which means costs and losses close to infinite. And so this is an indeterminate problem, very difficult to, let's say, somehow transfer the information to the society. Now, we have, the good news is, from the engineering point of view, we know a lot. I think that in the last years, we progressed in traditional materials as much as we know for modern materials like concrete or steel. I think we know almost everything at all scales, from the nano to the super big. We have amazing tools today with drones, with laser scanners, with inexpensive, easy to use, amazing software that allows me to get the 3D model very fast. We have amazing tools that are very similar to what we use in medicine. We can sense a building that our hands cannot sense. We can hear a building, we can see a building that our eyes will not see. So we have amazing tools that allows us to characterize the condition. How good is the building? We have more and more inexpensive tools to monitor. Everybody has an accelerometer in a cell phone. This is why the accelerometer knows up and down or where is north. And this is very inexpensive. You can have a triaxial accelerometer for a minimal cost. And we have amazing tools to simulate in our computers anything we need to simulate. Sometimes we don't have enough data, it is true. Sometimes we don't have enough money to study carefully. This is also true. We have to make choices, okay? But this is pragmatism, this is engineering. Engineering is about making choices, okay? And we have new exciting materials that are appearing every day. You know, sustainable materials, new materials that did not exist several years ago, or several decades ago. And so what we try to do today in structural engineering of the built heritage is to combine empirical evidence, so things which are more on the qualitative side, and our experience from observation with hypotheses that we put in sophisticated models to come to a conclusion. And this is quite different from modern engineering of modern buildings, where everything is known, or most of it is known. In an existing building, a lot of it is unknown, meaning we have to address uncertainty, meaning that we have to consider things which are based on our experience, based on our judgment, okay? So we have basically 3 steps: understand the building, understand the causes, address safety, is risk adequate or not, and then design measures if necessary, okay? The good news is that the codes are going in this direction. We have a lot of information available. I'm putting you here an example of the new code that is coming up in Europe in the next 2 or 3 years for existing buildings. Everything is there. We have information about traditional materials. We have complex information on how does, for example, a timber floor work. So there is information available, information we can use safely. Now, there is also a lot of things we don't know because they are complex. And this is why we still need research. And of course, why research makes sense to contribute to what we say a wealth-based society or a knowledge-based society, and to innovate, bring new products. And this is the base of a very large project that we're running now in my university, where we gather the best experts in the world, I believe, or some of the best experts, and we ask them to do a blind prediction on this building. It looks super simple, and it is simple. It's one facade, 2 retaining walls. You could see there was an earthquake, there is a shaking table moving, and you could see that failure is extremely fast, it's really fast. It moves and it collapses. Now, if you look at failure in slow motion, things are a little bit different. And it's really amazing how this behaves. You can see that it starts to go inside, and there is a beautiful V here going over the lintel, okay? So there is a crack, and this part is going inwards. Like when you brake, your body goes to the front in your car. When you accelerate fast, your body goes to the back. This is an inertial force. So this part is going, the gable is going backwards because of inertial forces. Now, when you continue, now it's going outside, you can see the V maintains, it's almost collapsing, not yet. Then the V opens again, and now it's going to collapse almost all, but no. And then in the end, it only collapses a part of it, and it continues. And when it collapses this part, it also collapses the back, as you can see. Oh, Jesus, doesn't matter. And it's super fast, okay? So the end point is that it collapses the front, the back, and it's super fast. The pier almost collapsed, but it's not collapsing. And this part is going to collapse next. So as you can see, this is a fraction of a second, and it's very brittle. Something structural engineers hate. We want ductile failures, failures which are safe. We tell people this building is unsafe. You can prop, you can do something, or you can run away. And so this is very difficult, even from the mathematical point of view. And as you can see, the experts were excellent on average, because the average is very close to the experimental, but they were a nightmare in terms of predictions. It's not really a nightmare. The good news is that most of the experts, 80%, predicted safe solutions. And so engineering is not perfect, is not in the case of dynamics of these very brittle responses, but we are on the safe side. But we need to know better. We did another example. This is more professional oriented. These are several commercial softwares, several of them widely used in engineering, SAP 2000, OpenSys, okay? Others less used in engineering. And we tried them to analyze 2 buildings. The results were not very good. And so you have the average, and we would hope all the solutions here, you can see 9 solutions, all of them would be at 0. And you can see large errors between minus 60 to more than 100% or the double of the error. So this is way too large. We do have problems with dynamics. Dynamics is very complex of these structures. This is the way we're trying to go in profession. we would like to have mechanisms that we change this complex system to a simpler system, and then we apply dynamics here. And here you can see the difficulties we have from the engineering point of view. This is the code application of dynamics of these systems. The codes in Europe allow that you adopt a force-based or a displacement-based approach. Problems. A force-based approach is dumb. It doesn't consider the scale effects. And so it doesn't matter if the building is small or very big. And if you use a static approach, the response is always the same. We know this is profoundly incorrect. Okay? And in dynamics, if you do it displacement-based, the capacity of this structure depends on its size. And so a small structure and a large structure have different safeties. Okay? Now, interesting aspects also. If I go back to this building and now instead of doing a code-based analysis, I use random earthquakes, both of code type or based on databases of earthquakes across the world, so that on average, I try to replicate the code. I see very nice things. And the very nice things are, again, we are predicting on the safe side, because I'm showing you here that all these predictions, the black and the white, doesn't matter so much. They are all on the safe side. Very few predictions are unsafe according to the code. No prediction was unsafe if I take the real failure of the building. Okay? Again, we have problems in dynamics of these types of buildings. This is a church we work in Cyprus. Well, this is a bit sophisticated. I don't want to go in any sophistication. We did the measurements in the building. We did the model that replicates the existing building. We applied the code. And by applying the code, we are able to calculate what is the target displacement for different scenarios. So almost no damage, the standard damage of the code, or full collapse. And so this is a code analysis, and this is a more sophisticated time history analysis. So the best representation of the earthquake. Again, you can see that the code will tell me 20 millimeters. The code will tell me here 120. And as you can see at the peak, I am at a very much lower values. So again, I'm on the safe side. This is good if I'm on the safe side, if I use more sophisticated tools. But this remains a true challenge for structural engineering. Dynamics are really complex. Now, I tried to somehow balance our activity in between research and practice. And research is supposed to feed practice. Of course, many things we do in research, we cannot apply in everyday engineering, okay? We are lucky to apply very sophisticated tools in very sophisticated case studies. This is, for example, a building in Isfahan where we worked. So it's an amazing building. There's these double domes from, let's say, Persian origin, are extremely famous from the point of view of building technology, shape, architecture. You can see it's a little bit of complex structure because you have, you have these stiffeners inside. Okay, this what you see here, it's a masonry stiffener, is this elements. And the masonry stiffeners are capital for the response. If you don't have it, the structure is rather unsafe. You can also see that the conception of the space is very different from what we often address as Western world. So we tend to have super huge buildings that impress from the outside. So you are having a demonstration of power, but then the building also impresses you from the inside and makes you feel very small. Whereas in many other cultures, well, this is an impressive building from the outside because of the scale, but inside they are very small. So if you go from the Taj Mahal inside, for example, which is a mausoleum, so it's let's say a house for a princess after life, inside is a super small building, because it is outside, which is important. And here's the same in this temple. And this double dome is because of, well, let's say, making you feel differently in this space. Now, there are many discussions, for example, if these timber elements are important for structural performance. My opinion is no. In some of these domes, they are not there. And in this dome, which they are there, they are not properly connected. So if you are asking, well, then why the hell they have these timber elements inside? It's very simple, because they use it to build the dome. And so this is to put some wooden planks and then to build the dome from the inside. And they were not removed because nobody sees them. So why do you need to remove them? Actually, they are even nice if you have to go there again. In any case, you can see here the example of the safety assessment we did for earthquake and for the new metro line that was supposed to have a station very close by. And here you can see cracks predicted in our model. And this is validation of our model against an experimental measure. This is another interesting example where we work together with Professor Mario Santana. I think he's here, I'm not sure, it's a small photo, but I met him in many places across the world. And this is a very interesting aspect in earthquake engineering. There was a low or a moderate size earthquake in 2016. Now, as you can see, it was minor, very few buildings damaged, okay? 4 people killed, which I would say compared to very large earthquakes with hundreds of thousands of people killed is a relatively small human loss, okay? For the ones which are more linked to earthquake engineering, you can see here some accelerations, and so they are super small. You can see 008G, and 008G qualifies as a low earthquake, okay? But the impressive thing is that, well, if you have not heard about Bagan, Bagan is the temple valley. It has, I think, over 3,000 temples in the valley. There was a huge destruction. And so even though there was very little damage in most housing, the temples suffer a huge destruction. Why? I believe because of dynamic amplification that affected only this type of building. And again, you can see why dynamics are so complicated. If you do statics, you'll never get this, okay? And these are some studies we did again to try to discuss the failure of these buildings, and many measurements done on site, and to see how it could have been possibly strengthened, okay? Another example of a building that is going to start on strengthening, I believe still this year, is the Ica Cathedral in Peru. It's a building that suffered 2 earthquakes of, let's say, this quite strong and this strong. There was a lot of damage, so the main vault basically vanished. The dome basically disappeared. The tympan is totally strengthened because it had major cracks. And here, I mean, from the social point of view and from the cultural heritage point of view, it was very important. I mean, for me, as a learning process, I had many discussions with me and, of course, the designer. I'm assisting the designer. I was not the designer. The designer is Professor Daniel Torrealba in Peru. These are very sophisticated models. It's probably the most complicated model I've ever done in a computer. But people here made me one of the most difficult questions that you may have to answer, at least one that I had to answer. And what they asked me was, why do you want to convince us that we should repair and use this building, which clearly is not safe? And why shouldn't we have a new building, which is as safe as all the other buildings that we're making now? And I mean, it's very easy for anyone to say, well, you can use the building, I'm doing it, I go away, it's not my problem. But the question is different, is can we accept people to use buildings with a very low safety level? My vision is clear. No, we have to accept a minimum level of safety. Otherwise, we cannot be responsible for the building. And so we did our best, and we believe that this building has a more than acceptable level of safety for modern use. Okay, and so there we made many simulations. Again, the interesting part is we are able to move from the unstrengthened model, which has this very, very fast collapse, as I showed you before in the video. So this will collapse, and then part of the building will collapse. And we can move it to a building that has a global behavior where damage occurs if there's a very strong earthquake. This is the idea of engineering. If I have a major shake, I need to have damage. It's not economical not to have any damage, but we protect lives. This is another example of a building that we worked that was attacked by blast twice. And again, I mean, what we tried to do, for example, was justify the damage here, and we could justify it. And then we defined what are the minimum distance that we have to ensure in order for the building to be safe. And so it is impossible, of course, to make the building safe to anything, but you can make it safe for a car-size explosive by providing a certain distance to the building. And this is what is normally done in profession, okay? And this is for another example that was done in our capital for the main train station. Okay, so different scenarios. And when the scenario is not acceptable, you have to do something about it, which in case of a blast, if it's of course a strong explosion, you need to be sure that you keep the distance. Okay. Now I'm going to show you fast a couple of applications. This will be a video, so super fast. This is the case study I worked longest. I presented when I was in Carleton. So it's the cathedral of the city I live. It's a very interesting building. Has been around for 800 years, of course, with many changes. We have been lucky to be sort of appointed as the structural engineers. And so we worked on many different places across the years. Okay. The last works we did were here. And I mean, last is really last year. So it was super recent. Okay. I'm going to show you a few examples very fast. So this is some inspection of the towers. This is the constitution of the walls. These are very thick walls, about 2 meters. The walls are made of 3 leaf. And so there is a big core, and the connection between the external leaves is impossible. They are too big. And so it's very bad, in fact. So there was huge cracks. I mean, this crack is 25 centimeters. I can put my hand, my full hand inside. I don't reach the end. There are many cracks, a lot of bulging, ties which are broken from the past, and continuous movement because we can compare with old photos. So the situation is not very nice. And basically we introduced a system, which is a set of internal rings, which are connected by ties to the outside. So the system is partly invisible. There's a few crosses. In this wall that was a disaster, there's a few crosses and a few plates that are visible. And we tied the wall from inside. We tie the tower from inside. These are some examples of the execution. I will not go into many details. These are modern materials, all stainless steel, the most expensive, injection tubes in order to inject the material inside the holes and to have proper bond. And I mean, what I found amazing here is, for example, the Lego construction that an engineer has to think of. So this is very easy to put in a drawing. The problem is how we're going to build it. And so we designed a system that the parts were small enough to go through the window or through the door, and it could be built inside without any difficulty. Everything was pre-designed, everything was bolted. There was no welding on site, zero. Okay. So these are some details of the execution of the elements. And here, I mean, I liked very much this book because, you know, now is the Patriarch of Lisbon. So he's one of the few cardinals and patriarchs of the Roman Catholic Church. It's a very important position. And he loved very much the crosses of an engineer. And he put them in his book, okay? So I think, I mean, our things should be visible. And of course, they should be pleasant. Now, another example that I'm going to show you briefly of our detective work. This is in the same building, is the skylight, which has a bit damaged, not going into details. There's a few cracks, a little bit dangerous also because there's no support for these stone slabs. And the detective work here is, why do we have this damage? And we did many analyses, self-weight, no damage. Additional infill, because there's a lot of rubbish that people put in the buildings if nobody sees. No damage. Temperature effect, almost no damage. So where is the damage coming from? And this is what we have to do as engineers of the built heritage, detective. And then, well, I start thinking, this is not the problem of the transept. This is the problem of the building. And in fact, because the foundations are poor, the problem is the foundations. And it is the foundations that destroy the upper part. And once we know this, very simple to decide what to do. Another example of our difficulties. This is the damage in the back facade. It was our last intervention, moderate size cracks, previous repairs, okay? Well, some of the cracks in the vault are not so moderate, a lot of damage, okay? And we find, well, some mapping of the damage, and we found some complicated stuff. I'm not going to talk about it. I'm going to talk about complexities. I'll show you two complexities. This seems super simple. I mean, we are designing a truss. Any second-year student can do this. It's not that simple. Why is not that simple? Because the space we had to work was minimal. Because we had to comply with the existing level of the roof. We wanted to remove load. And so we had to clamp this here on this side. And this is the clamping system. We had 8 centimeters to work of space. And we had to be sure that we're not going to put load in addition to the vault. And so even though this looks super simple, I can tell you it took several weeks to do a simple, very, very simple design. It's not so simple. And it was built in pieces and in 2 pieces and brought by a crane. Another example of our difficulties. This is a church that we act in Coñotambo, also in Peru, that it was finished a couple of years ago. I was there also with Professor Santana. There's a lot of damage because of deterioration, damage due to earthquake, damage due to soil. Not going to do into details. We did a sophisticated model. Our model predicted the existing cracks, super nice. We're validating the model. Then we did extremely complex intervention together with Professor Torrealba. And you can see all these timber connections inside of the adobe. So we're using traditional materials, only timber, only earth, but properly. And then there's a few nice details. For example, you don't see this much. If I want to tie the roof, I need some anchor keys. And in many places you see anchor keys outside so that the tie works. But I want a special tie. I want a tie that works as a tie, but as a strut. Because when the earthquake comes, I need a strut. So I have to put anchor keys on both sides. If you fail to do this, it's not going to work. It's a disaster. And so again, what we tried to do was to move from this very brittle, very local failure mode to a global failure mode where everything works together. There are many technical, interesting details. I'm not going to speak about this. These are some photos of the works done. I'm going to show you this. This was another similar church that had been repaired. In the week before the inauguration, an earthquake came. It was a local earthquake, and you can see the condition. The works were not done properly. It was not adequately tied, not sufficiently keys. For example, this is a disaster. It's a basic earthquake engineering error or structural error. You cannot have a buttress, this is a buttress, connected to a wall without tying it. You need to tie it carefully, like we are doing here. If you don't tie carefully, the batteries are not working together. If you don't tie the corners properly, it's not working together, and you have a disaster. And so this is not what we want to do. Okay. Another second example, very simple. I have a few examples very fast. I think I have about 10 minutes. This is a very important monument. You have the tombs of many kings in Portugal. You have many reliquaries from many saints across Europe. And it's a very steep roof. We worked here in this roof. And so the roof has inside as a vault or a cupola. And if you have this inside, you cannot have tie beams. And so a roof works beautiful when it has tie beams. If there's no ties, you have a lot of thrust. Okay. And so there is a bit of damage, and we tried to keep the roof. And so we tried to install a few new parts and do some repair. And the owner said, and the heritage authorities, forget about it. We repaired this roof 20 years ago. We still have a lot of damage in the vault. We don't want this roof. Let's put a new one. And here you can see a huge deformation in addition to attacks, and you'll see it next. It was a good decision. So something that looks super simple. I mean, anybody can design a timber roof. Simple. I can tell you a couple of months work, super difficult. Because I have something inside. The geometry is predefined. These are huge spans. If you're a timber expert, this is 15 meters. This is about 13 meters and a half. It's very big, okay? So in order to reduce the span, we use these trusses on the side. All the space inside, we are not having anything. It's because we have the vault, okay? Then we put this inside. We put these very strong rafters, which are connecting and helping this ring. And all of these additions, the red one, the truss there, is to reduce deformation, because this was not complying with any deformation requirement, okay? And again, this will be very, very close to the existing vault, so you don't want to put load on a vault which is very light and cannot deform. So it looks simple, it's not simple at all. We did even another trick, which is interesting. We put the thrust or the reaction of this very big trusses. We did not put it in the wall here, and we put a steel element long to move this thrust to the sides in order to reduce the bending moment of the wall. Very simple, but we put a new steel element, which is this one, to move and transfer. Let's say keeping the shear, but reducing the bending moment of the wall. Okay, very simple design. This is, you can see the huge deformation. So there are many past repairs in order to be able to accommodate. And this was deforming, destroying the vault inside, really destroying everything. And so these are the execution. This was all made with solid wood, no CLT or no laminated timber, but it is what it is. It could have been obviously glue lam without any problem. And so these are some details of the execution. Now, I'm going to show you another example of complexities. This is a reinforced concrete element that collapsed. It's very simple. It's a cantilever, but in this very simple thing, we have about 50,000 people living, because this is social housing, all built in the 60s or 70s. There's a lot of problems, including wrong RC construction, deterioration, etc. Okay. Now, the interesting part here is the relation with society. And so, I mean, the TV was there, the newspapers, the mayor was mad. They had already invested a lot of money in rehabilitating these buildings, but this was all painting and changing, facades, and very little on the structural, nothing. And so they asked immediate action. And I said, I'm not going to do anything before we study. If this has been around for 50 years, the risk is very low. If there is another event, you're going to prop everything tomorrow, okay? And so we have an initial budget for 10 million for only strengthening the balconies. And in the end, we do it by $1.5 million by studying and doing properly. So we develop a testing plan. In some buildings that are being repaired, we installed immediately a very simple strengthening with new reinforcement, and that's it. This is super inexpensive. super easy to do. There's no reason not to do it, okay, if you have doubts. And then we have complexities because many of the buildings had been repaired, and so we had to do many things. There were many complexities. Sometimes we put things from above because this was possible. Sometimes we put things from inside because this was the easiest way. No interaction with whatever was already finished. And so this is, I think, interesting to show you the ability we have in order to do complex works by using modern engineering. We can do things which are invisible, we can do things which are visible. In this case, the cheapest one is do visible from below, but normally we cannot do it. But when we could, we did, and it's beautiful actually. I think it looks very nice. And this is the cheapest, and when we could do it, we did, okay? Now, I end up with another type of approach because I told you about different tools at different scales. These are some examples of studies we have been doing at territorial level to manage risk. Now, in this case, for example, if I have here a vulnerability index, this means this building is vulnerable. This means that for, you know, for a given earthquake, the red building will have a lot of problems. Well, the green, no problems, the yellow, no problems, okay? Now, I do not care if I'm doing a city or world scale study, if this building is yellow. I don't care if this one is red. I do care on how much money I'm going to spend. And I do care on understanding the vulnerability of the territory, but not on individual buildings. So I want to be correct on average. I don't need to be correct on the single building. I use very simple tools. And I can do this that we use for planning. For example, for a certain scenario of a disaster, how many buildings are going to collapse? How many are going to be impossible to use? How many people die? How many bed hospitals you need? How many tents, how many temporary housing you need? This is super important for immediate action, okay? We can also do these studies on designing and defining retrofitting packages, and then I can do the same. If I do a retrofitting, how do I change vulnerability? Then what is the consequence of using retrofitting package 1, 2, or 3 in the number of dead, in the number of homeless, okay, in the number of buildings that collapse or are unusable? I can even do this, which I think is a super important graphic for society. I can show society that if you put money in the long term, you gain money. Or I can show society, if you put money, you lose money. And this is a decision from the society. You can say, I don't accept living with this risk, and because of that, I'm going to put money. Or you can say, no, if I'm putting $1 now, I'm going to spend money, I'm going to use less money in the future, and then I need to do it because it's my responsibility to invest money to, let's say, spare money for the future. And this is a very important decision. Do I accept to live with, let's say, higher risk, or do I need to act now? We can also support emergency planning. For example, defining which part of the building of the city is not usable, which part of the buildings will collapse and I cannot access. If I cannot access, people cannot exit. And I cannot go there with the firemen. I cannot go there, you know, with the people, with the ambulances. And so I need to have evacuation routes, and I can work selective to reduce it, okay? And this is another example of addressing, you know, territory. In this case, is the full railway infrastructure for terrorist attack. And we use very simple tools. I can define scenarios of attacks. I can apply a very simple risk approach where when I get a certain number, like I showed you before, when I get a certain number is not acceptable, I have to do something. Or if I get another number, I do something else, okay? My last slide, I think I'm more or less on time. Well, conservation engineering is a very exciting field, as I tried to tell you. What we have built is around. What we have built defines us as a society. What we have built is important for our economy. Any extreme event is a challenge. Existing built heritage is a challenge because there's a lot of things we don't know. There are many interesting questions in green that I do not have an answer. It's something that we have to look into. One aspect is how to handle the economic value of buildings with cultural value. Complicated issue. The second aspect that I tackled very briefly in this my last slide with the costs. We know it makes sense to put money to save money. How can we enforce society, ourselves, to put money to save money? Very difficult. The last point, because I'm assuming I'm talking mostly for engineers, we have all the tools now. How can we communicate properly so that people understand the simplicity of the problem and the complexity inherent in order to be sure we have more resilient societies? Thank you very much. It has been a pleasure.
Thank you very much, Professor LOURENÇO. Such an outstanding and interesting presentation. Now I think we will accept to have some questions from our audience. So yes, so I have the first question here. Okay.
Do you want me to answer, or are you going to read it?
Yeah, okay. So I will basically direct you from this Q&A window. We have the first question, which Sharma is asking. So simply, outstanding presentation. They're thanking you right now, and we'd love to hear more from you and details on some of your solutions to the problems. So I mean, I think we have a very very nice presentation about lots of solutions. We have another question. Sorry, could you please elaborate why you use visualization aside from simulation in the field? Is it just for having an original 3D model of the current situation? So what is the significance, in my opinion, the question says, the visualization in the structural simulations?
Okay, thank you. Well, I would try to address a couple of different aspects in the question, which I'm not sure if it is the objective.
Okay.
Now, one thing which is important is obviously whenever you have any building is to have a proper geometrical survey. Okay.
Okay.
And so a geometrical survey is necessary because you need things like plans, elevations, so that you can mark when you go to the job site, because you need to map things and to understand them. When you are in the building, you are often lost. To make it worse, you cannot see the front and the back, and you cannot see this division and the next division. So you need to look into things which you have mapped, or they have been mapped into plans and elevations in order to understand many of aspects related to the condition. And we are having really, I would say now, amazing tools, as I said before, that allow us to do cheaper and faster, okay, better. A second issue, which it is not, I think, often clear to people not in the field, is that a geometrical survey is sufficient for an engineer, structural engineer. We need to know the morphology. We need to know the details. For me, it's not relevant to know that I have, let's say, a roof or a floor if I don't know what is the composition of the floor. Often you have drawings that have the lower part of a vault and nobody knows what is on the upper part. And so this is irrelevant. So I need to know what is on the upper part. And if I see the upper part, what is structural and what is non-structural, okay? And so I need the geometry. I need the morphology or the details which have to be mapped. And these are then considered in a structural model.
Right.
And in the structural model, then I do the analysis. And again, I have to understand the results and to communicate them in a way that people understand. And when you go to very sophisticated models, obviously, if you do a simple hand calculation, you are under control. When you do a detail, for example, a truss or a cross section of a building, you are more in control. When you're going for 3D, you really need to be careful in presenting things carefully. And normally when I'm doing things together with my coworkers, when we're discussing the results, we sit together or we do it via Zoom and we are moving the model together because I need to do sections, I need to do zooms, I need to do many details in order to understand how the building responded.
Right.
So I try to answer.
Yes. Yeah, no, that's very good. And we have another excellent question here. Juan Salinas asking, can the knowledge of the potential dangerous behavior and its consequences be incorporated into our pedagogical activities? Can we incorporate this into our teaching? It's also it's a nice point since I'm also teaching conservation engineering at Carleton University. So that's quite an important point. What you will say about this problem, Professor?
Well, thank you. It's a difficult question.
Yeah, it is.
I mean, I don't know what is the situation in Carleton. My impression in most universities across the world, including mine, is that conservation receives moderate to low attention. One reason being that anytime in engineering and architecture course, technical details tend to be reduced and replaced often by less technical. I mean, I'm not saying it's not super important to address super important issues, including management, costs, soft skills, sustainability. This is all very important, but we're losing often the mechanics. And we're losing the built heritage. And so I can show you the European market in construction. 50% of the construction market in Europe is maintenance and conservation and rehabilitation. This is 50% of the market. It is more on the former Western Europe and less in the former Eastern Europe. This means 50% of my students, half of the classroom is going to work in the built heritage.
Right.
And we don't train them for this.
Right.
How to change this, I have no idea. And so how to bring more lessons from the past, we try to do it in seminars, in capstone projects, but we find a lot of troubles in putting more to reduce something. And this is, I think, everybody's facing.
Okay, yeah, thank you very much. So we have another question. So Ashwati asking, even after careful study and evaluation of the structure, is there a possibility of dynamic loading during strengthening process causing unexpected damage to the structure, local or global?
I think the possibility, if I understand the meaning of dynamic, it depends what we mean, of course, with dynamics. Because, for example, a simple example is when you have a deteriorated roof and the deteriorated roof collapses. It happened to me in the sense that I visited the building 2 weeks after I went there and the roof was no longer there.
Wow.
And so conservation can also be risky, let's say. But it is what it is. But what I'm saying, if a roof collapses or a floor, it's a dynamic process that normally induces other damages because of dynamics. But if I think about dynamics induced by an extreme event like an earthquake, I would say that this is extremely unlikely because the probability that you have an earthquake in the moment you are doing the intervention is 0. Now, if the question is different, which is possible, which could indicate a dynamic action because of an incorrect intervention, and so we are triggering a mechanism unexpected, this is a different issue. And so we do, according to the, let's say, the international attitude towards conservation and the charters and recommendations, it is said that any action you cannot control, you cannot implement.
Yeah.
And so you have to be careful because, of course, we are doing, for examples of things which are on the a bit crazy side. For example, injecting a grout.
Right.
If you inject a grout, you're putting water inside. So there is pressure. Of course, normally we inject at very low pressures.
Right.
Okay. Almost, atmospheric pressure in the end, but it's maybe 1 bar, so 10 meters. But if you're going to inject like you do in concrete at several bars, you're going to explode the wall. You cannot do it. Or if you want to inject, from the very high top, you must be crazy. Huh?
Right. Right.
Other examples, for example, if I have a risky operation, I am sure I have a control. The control can be, for example, topography.
Right.
For example, I use a jack with a load cell, and I know I moved walls. No, I lift bolts. I know, of course, together with a team and with a lot of amazing workers that made this possible. But we move these things, and you have to be careful. But nobody is going to lift a vault or move a wall if I'm not present. I think if you are the structural designer, you have to take responsibility and be sure you measure the consequences.
Certainly, certainly. So we have another question. Farooq Fazileh asking. So thank you for a very interesting presentation. Could you please elaborate a little bit more on the definitions of safe and collapse of buildings under seismic loads in European context, as it seems to be different from the Canadian code requirements. So what will you say about that?
It's a detailed question. I think they are the same. Maybe I present it in an oversimplistic, some people can say wrong way. I would rather using oversimplistic. What you do, particularly for dynamics, is to talk about normal performance criteria. That will be 3 or 4. Normally, our European code for earthquake performance of existing buildings, we consider the 3 criteria, which means immediate occupancy,
right,
or light damage and significant damage and near collapse, something like this, depending on. And we typically do performance-based, meaning displacement assessment. So some of the things I showed, they were very fast, but theoretically, you can apply it.
Okay.
And even if you do it force-based, for example, for a mechanism of a local collapse, which you have in a building, which is made of masonry before you strengthen it. And so even if you do it force-based, you can try to do it by using, let's say, behavior factors that take into consideration the dynamics.
Right.
A different question is cultural heritage, where there are no codes in Europe, and I believe the same in Canada, except of Italy, to my knowledge.
Yes.
And so cultural heritage, according to the European code, is a different type of building for which the codes do not apply because they have very, let's say, abnormal or outstanding structures, different from the usual.
Right.
And so for a cultural heritage building, which our code in Europe says nothing about it, the code in Italy allows something different, which is, let's say, precluding local losses like a chimney, let's say a spandrel, and increasing the condition. So in case you are not able to do anything, at least you are putting it better than it is. For example, for an existing building, non-cultural heritage in Europe, typically you don't enforce the same safety level as a new building, and we enforce a safety level in the range of 70%, because normally you reduce the demand about 80%, something like this, and then you say that you only have to strengthen in case that, you don't comply, if you don't reach 90% of the expected performance level. So I think it's exactly the same as Canada and US.
Yes.
Maybe I presented a bit oversimplistic.
No, that's all good. Actually, it is 11:30 22 right now, and I don't see another question in the Q&A. I have just one very quick follow-up question. Simply, you talk about this dynamic analysis and the blind test predictions, and it seems that our predictions are mostly safe on the safe side. But I mean, we most of the time we ignore to model soil at the same time the structural simulations. So I was wondering, what are your thoughts about soil structure interaction simulations that we have currently in the literature? What do you think about it? Are we doing good, or still our predictions when we consider the soil in the simulation still conservative? Or what are your take on this?
It's a very difficult question. I mean, even though, you know, civil engineering is a long established profession, often we put things into small baskets. And
Right.
so hydraulics are normally very far away from structural engineers, not all. Geotechnics is very far away from structural engineers, again, not all. And so this makes it complicated. It is not unusual that a model of a tunnel or of, let's say, or slope stability, you know, in a geotechnical engineer will be often extremely concerned about the soil and use advanced models if this is the case. And the model for the building is simplistic. And the structural engineers tend to do reverse with a very complicated building for the structure, very simple for the soil.
Yes, yes.
Well, let's say, again, in profession, in most buildings, certainly the soil is taken into account, and the earthquake demand depends on the soil. In most codes, you will take into consideration amplification due to the different strata and the bedrock location. In some other codes, I'm not sure about the Canadian, but in some other codes, you take into consideration the topography. In some codes, you don't take.
Okay.
And so it is taken into consideration in dynamics. Now, if we're talking about considering the dynamic effects of the building and of the soil in reality at the same time, very few people do it. It can be important for very specific structures. Obviously, particularly in the case that the frequencies are somehow related from the building and from the foundation.
Right.
But it's over complex. In reality, we hardly use dynamics in engineering. By dynamics, I mean time history analysis. We use dynamics for sure, but time history analyses are extremely complex to apply because of the requirements in defining the action and in defining performance, which is also not simple.
Got it. Okay. I think, yeah, I mean, we are at the end of the Q&A session. I would like to thank you one more time, Professor LOURENÇO. It is such an honor to have you here today in our
I thank you,
lecture.
Carleton, and all the presents, of course.
Thank you very much. So I think I need to give the floor to Siva, right?
I will start now.
Yeah, okay, go ahead, Jack, sorry.
Well, thank you, ladies and gentlemen, for those questions. And then thank you, Dr. LOURENÇO, for a remarkable presentation on the work you've done, which is equally remarkable. And thank you for accepting our invitation. And at this time, it is my pleasure to invite Professor Adjeleian to present on behalf of the university, the department, and indeed, in behalf of all of us, a small token of our appreciation to you, Dr. LOURENÇO. Ehab, please go ahead.
Thank you. Thank you. I think by now you received so many thanks. I thought, well, there has to be something, you know, touchable. If you can see my shared screen, it's actually a very small token of appreciation. The Department of Civil and Environmental Engineering has created this beautiful plaque that has also a beautiful picture of one of the John Adjeleian famous projects. It's the National Arts Center here in Ottawa on a wood piano finish. The actual picture is actually more vibrant than this. Just, you know, taking a picture from a picture, it doesn't show the beauty of it, but this will be our, you know, token of appreciation. It has your name and the date of today's lecture, and it will be mailed to you. But just be patient, the supply chain and the mail is late. I'm trying to talk to the chair of the department if they can pay for my ticket to deliver it in person to your warm country. I'll be happy to jump in on the next plane. But thank you so much.
Thank you very much. You are all welcome to Portugal and Guimarães. Guimarães is the cradle of Portugal. So it all started here in 1128.
Thank you, Dr. LOURENÇO. This is a plaque that we give to our speakers every year for the last 18 years. There's one copy of this plaque is kept on is hung on the wall of fame of the department with the names of all of the speakers of the past. This one also will come with your name, and your name will also show up on our wall of fame plaque. So thank you very much. I know it's a very small token of appreciation, but the physical distance between us makes it difficult to really do more justice to it.
Right.
Now, it's been a tradition with us to use this opportunity to honor those of our graduate students who have excelled in their academic work and have received awards in recognition of their work. It is not possible for us this year to present these awards in person because of the COVID, of course, But Professor Adjeleian will read out the names of the winners as well as recognize the sponsors of those awards. Professor Adjeleian, the floor is yours.
Thank you, Jack. Let me share my screen. Yeah, Mrs. Adjeleian, Professor LOURENÇO, ladies and gentlemen, it's a pleasure to have this opportunity to present these awards to our students who were recognized or who are recipients of an award this year, either from the department or the university. The first award I have here is Jack Morgan Humer Graduate Fellowship. This fellowship was endowed to honor Professor Emeritus and Chancellor's Professor Jack Morgan Humer, who's our Master of Ceremonies here today, for his service to the university, profession, and the community. This award is given to an outstanding student in the department, and the recipient this year is Amir Tabatabai. Next, I have Professor Atta Khan Sustainable Transportation Scholarship. This is endowed to honor the contributions of Professor Emeritus Atta Khan and is awarded to a student in the area of sustainable transportation. The recipient this year is Seth Gatian. Next, we have Dr. Abdul Halim Memorial Scholarship. This is endowed to honor the memory of late Professor Abdul Halim, who has served our department in various capacities, including as the chair. And the scholarship is awarded to a student in transportation engineering, and the recipient this year is Ali Isian. Then we have the John Breaksma Transportation Scholarship. This is endowed to honor the memory of late Professor John Breaksma, and it's awarded to a student in transportation engineering, and the recipient this year is Alisa Bernier. The Society for Fire Protection Engineers National Capital Region Chapter Scholarship for Fire Safety Engineering is awarded to Fatima Mehrapur. The Alfred J. Weiss Scholarship is awarded to a student in Fire Safety Engineering, and the recipient this year is Sanaz Ramziaragi. Gordon Shields Memorial Scholarship is awarded to an outstanding student in the Building Engineering program, and the recipient this year is Fasam Kavari. The Kochar Scholarship, endowed by the Kochar family to support students joining from India, is awarded to many students each year, but due to COVID situation, we only have 2 of the recipients here with us this year. They are Aravind Murali and Akshesh Kumar Nalin Kumar Patel. And the last departmental scholarship I have is the graduate scholarship in civil and environmental engineering. This year we have awarded to a civil engineering student. This is established by the department to recognize an outstanding student joining the graduate program upon completion of a bachelor's degree at the department. And the recipient this year is Gabriel Karam. And the next list of scholarships are university-wide awards. And the winner of the Indira Gandhi Fellowship this year is Pedram Nojadehi. The winner of the John Raptash Fellowship is Brandon Robinson. And the winner of the Carleton University Academic Staff Association Scholarship is Brody Hobson. And the Mary Carter Memorial Scholarship is awarded to Sepide Mirshekar Siakal. And Irene Ethel Cockburn Bursary is awarded to Ankush Kandalwell. And the Queen Elizabeth Graduate Scholarship in Science and Technology is awarded to Nagesh Torabi. And finally, I want to mention, we normally start this award ceremony with the John Adjeleian Graduate Scholarship. This year, our event is happening a bit early in February. So the John Adjeleian Scholarship recipient hasn't been decided yet. So that this process is in progress, and we will identify a recipient in the coming weeks. So these are our scholarship winners. And on behalf of the department, I would like to thank our speaker and the committee and Mrs. Adjeleian once again for giving us this opportunity to present these names at this event. Thank you very much. Back to you, Jack.
Yeah, thank you, Siva. Thank you for that recognition of our graduate students who have excelled in their work. Now, as we near the conclusion, I would like to once again thank all the audience participants who joined us today and had questions and answers session participating. This, as you probably know, is being recorded, and the lecture will be recorded and placed on the website of our department. So you can probably study it in detail later on. With all of the pictures will be there along with the audio. I would like to take this opportunity to express our thanks to all those who worked tirelessly along with me on the organization of this evening's lecture, evening in Portugal, almost morning in Ottawa. They include members of the organizing committee who are with me, Professor Yvonne Kim, she's here, Professor LOURENÇO, you of course have heard him, and Professor Ehab Zalok. Thanks are also due to Professor Sivathalan for recognizing our graduate students. And the special thanks are due to Ms. K. Castleman, undergraduate administrator, and to Ms. Reynosa Sarmiento, administrative assistant in the department, both of whom devoted many hours to the organization of this event and whose contributions are largely responsible for its success. I would also like to acknowledge the support of the departmental chair, Professor Yasser Hussain. Each year, for the last 18 years, I've been doing this. And each year, I invite all of those present to join us for a reception. Unfortunately, I cannot do this this year again. Last year also we missed. But rest assured, if you come back next year, we will have a grand reception for you. Thank you very much once again, and goodbye.
Thank you very much. Bye.